Welcome to the fourth part of this OpenFOAM tutorial on shotSleeveModeling. In the last part I took you as far as making the mesh able to move appropriately as we intended to do, and we will now proceed with actually adjusting all the necessary boundary conditions, and we do this by opening all the files that are in the 0 folder. Because this is where all the boundary conditions are placed at, and we can see that we still here have all the boundary conditions from the case of the slushing 2D tank. And let's start with the alpha melt first, or alpha water as it's still named. We will soon rename it into alpha melt, and we just rename this into front and back. Type empty, and this is about the walls. It can basically stay, but I just want to put it as a regular expression. So it covers moving walls, fixed walls, slip walls, and of course the outlet. Okay, this is that. Save it, close it. One down, some more to go. Point displacement we can already close. This is already fixed, as we saw last time. For the pressure, once again, front and back is empty. And here we have to be a bit more careful, because we not only do we need to change the patches, but we also need to change the value. We can do basically the same as we did in the last file. Moving walls, slip walls, fixed walls, and the outlet. Okay, so far so good. Save it, close it, and move to the next file. Front and back. Delete this or leave it just as you wish. And for the moving walls, fixed walls, the slip walls, we can use the fixed flux pressure boundary condition, but and also change the value, decrease it by 1 order of magnitude. However, for the outlet we need to have a sort of special patch, namely the total pressure patch. Outlet, and this is of type total pressure, and this actually needs a couple of entries, such as P0, U, phi, rho, psi none, the last entry is basically only that partIV won't complain. Okay, so that was that file. The T file is once more rather simple then. So there we have zero gradient at all the walls. The outlet too. Part for the back. Can simply delete, save it, and close it. Okay, the U file. We still have to do some adjustments. The walls we can rename into moving walls. So this is okay. We want to have the moving wall velocity there. The outlet I have to redo, and the outlet will be of type pressure inlet outlet velocity. And once again, for partIV, we need to specify a value here. 0, 0, 0. Okay, so that won't complain. And finally then, we also need to include one more entry for the other walls, namely slip walls and fixed walls, and for those they will of course be of type fixed value, and value will be uniform 0, 0, 0. Okay, good. That should do the trick for that. Next step will be adjusting gravity. For this purpose we open all the files in the constant, folder, constant G to start to begin with, and the gravity is now going in -y direction, so y minus z as previously. Can change this by doing this operation. And the other thing we need to adjust will be, of course, the other files in here. Let's start with the turbulence properties. There we have to go for RAS model instead, and the RAS properties are not laminar anymore, but we will instead use k omega SST. I'm going to need 2 more files for this turbulence model, but I'm going to address that in a minute. G, we're done. RAS properties, thermophysical properties are still to be addressed. And the Pmin, I choose to pick 100 here, and the sigma we also need to adjust in order to have the proper material properties for aluminum. We also can change the phase into melt here. Save. Sorry, it was actually 1000, it was fine. But this was 0.629. Okay. Done. Next one. The thermophysical properties. Sorry, I opened the wrong thing. Thermophysical properties water, or melt, as I'm soon going to rename it. And equation of state, I decided to go with rho constant here. Rho constant, and change the rho here into 25,075. The rest mu also needs to be adjusted. Prandtl number can stay, HF can stay, CP can stay, rho we already adjusted. Okay, this is looking good. Save it. Air are so thermophysical properties of air are the same. Turbulence properties we adjusted. Thermophysical properties we adjusted. Plus properties. Okay, let's have a quick look on what we forgot. Let's first delete all the or rename the 0 alpha water into 0 alpha melt.org. So that worked, that is good. And then do the same with the 0 alpha, oh no, sorry, not 0 constant thermophysical properties dot water into constant. Okay, that worked. So let's try, we can actually run the case. Well, I'm sure that there is at least one thing missing, but just to double check that I'm not missing anything else. Okay, so it's looking for alpha melt. Okay, well that makes sense. So let's just create it. Keyword rho is undefined in melt mixture equation of state. Didn't I just define it, or was it something else? So I gotta look into this once more. Ah, it's for 0. So that explains. Okay, that looks good. Alpha melt is undefined. Okay. Let's do one simple trick here. Let's use the set command in order to replace it in the system FV schemes and the system FV solution. Otherwise we would have to do that by hand. Try it once more. And now it's already looking for the K. Okay, so it makes sense. We need the K and the omega for the boundary conditions, and since we don't have them, let's Let's do that grep. Oh, I've got quite plenty of these. Well, that was a bit stupid, but I'm gonna correct the error. I'm gonna grep for k omega SST, and then I can find the files in the same folder. Okay, this is already looking good. It's apparently a very popular model. So if I take this file, for example, in the 0 folder, there should be the k and then omega. Okay. Same with an omega. Open these two. And once more, adjust them accordingly. We don't have an inlet, but an inlet. But we have a lot of walls that we want to include, and it's basically the same thing for all the walls, and the only difference is that let's just put the internal field at a very low, because we have a melt that is basically not in motion at all. Okay, so let's just go for some standard values that I determined. We have the moving walls, slip walls, and the fixed walls, front and back, of course. Type empty. And the outlet, of course, and for the outlet I'm going to go for the 0 gradient condition here. Okay, atmosphere we don't need here. And for the walls I'm going to use some standard boundary conditions that I found out to be quite good. First of all, it's compressible. KQR wall function. With the parameters of internal field, so this can stay. Okay. Okay, save it, and let's address the omega file. First of all, once more, take out the stuff we don't need. And here also 1e minus 5. Front and back will be the easiest of course. And the walls are the same once more. Slip walls. The outlet, 0 gradient. atmosphere we don't need, and this will be omega wall function with a value into our field. We'll additionally need to specify the parameters CMU at 0.09, kappa at 0.41, E at 9.8, and beta 1 at 0.075. Alright, that should be that. Okay, so now we can save that too. The only thing that we now need to add probably is some additional lines for the FV schemes and the FV solutions. What we're going to find out about that in a minute. Oh yeah, or probably, well, maybe there was a front and back. Empty. Was there a typo in there, maybe? Okay, so it was probably in the omega file. Yep, and it was a typo. So let's look at it one more time. Okay. Is that? Okay, and try. Let's see. What's going on? Okay, so diff row phi omega is undefined dictionary diff schemes. Okay, well that makes sense. Let's just edit. System actually. And the entry it once was diff phi diff phi omega diff phi omega, and also diff phi k, probably. And most certainly it would also sooner or later ask for it in the FE solution, so we can just edit here, similar with the U, that we can just add the omega and the K. Okay, there's that. Let's look at this once more. Okay, rho phi omega is also undefined. So let's get back to the FV schemes. Let's just copy that. Save it. See if now starts the solving. That is looking good. Kill it once more, Control C. And let's look at the, before we finally go, look at the system control dict. Everything's right in order. Let's see, okay, well, delta t might be a bit slow. I'd like to increase that a bit to at least 1e minus 5, and the right interval we change to time step, and I think I want every hundredth of a second I want a time step written out, so that would make 1e3 appropriate here if I have a delta t of 1e minus 5. So that should be okay, general, right? Let's have it run, let's give it a shot. And do the compressor to pull in the info once more. And while this is running, I can conclude part 4 of my video tutorial, and I will be back to you with post-processing in part 5. See you then.